Have you ever looked at a complex electrical circuit filled with resistors, inductors, and capacitors, and felt overwhelmed by the differential equations needed to describe its behavior? Imagine a method that transforms these challenging time domain problems into simpler, algebraic equations, making analysis significantly more straightforward. To write RLC circuit equations in the S-domain, you fundamentally convert each circuit element from its time domain representation to its equivalent impedance in the complex frequency domain, or S-domain, primarily using the Laplace transform. This process allows you to replace differential equations with algebraic ones, greatly simplifying analysis. The core reason this transformation is so powerful lies in how the Laplace transform operates on derivatives and integrals. In the time domain, inductors and capacitors are described by differential and integral relationships between voltage and current, which lead to complex differential equations for the entire circuit. The Laplace transform converts these time domain operations into simple multiplications or divisions by the complex frequency variable, S. Specifically, a resistor's impedance remains R, an inductor's impedance becomes SL, where L is its inductance, and a capacitor's impedance transforms to 1 over SC, where C is its capacitance. This eliminates the calculus, allowing you to use familiar algebraic techniques like Kirchhoff's voltage law or Kirchhoff's current law, much like you would for a simple resistive circuit. To actually apply this, you will follow a clear process. First, draw the circuit in the S-domain by replacing all time domain components with their corresponding S-domain impedances and all voltage and current sources with their Laplace transforms. Ensure you also incorporate any initial conditions for inductors and capacitors as equivalent voltage or current sources. Next, use standard circuit analysis techniques, such as nodal analysis, mesh analysis, or superposition, directly in the S-domain to set up your algebraic equations. Solve these equations for the desired voltage or current in the S-domain. Finally, apply the inverse Laplace transform to convert your S-domain solution back into the time domain, giving you the actual circuit response. A key advantage of the S-domain approach is its inherent ability to correctly account for initial conditions within the transformed circuit elements. For instance, an inductor with initial current can be represented as an impedance SL in series, with a voltage source representing L times that initial current, or as SL in parallel, with a current source representing the initial current divided by S. This seamlessly integrates initial energy storage into the circuit equations. Furthermore, the S-domain method is not restricted to sinusoidal inputs, making it incredibly versatile for analyzing circuits with step functions, impulses, or other complex waveforms that would be very difficult to solve using phasors. Mastering the S-domain approach provides an elegant and efficient pathway to analyze even the most intricate RLC circuits. By converting differential equations into manageable algebraic forms, it not only simplifies complex calculations, but also offers a powerful conceptual framework for understanding transient responses, stability, and frequency dependent behavior across a wide array of electrical engineering applications. This method fundamentally shifts your perspective, transforming intimidating calculus problems into solvable algebraic puzzles, ensuring you gain a deeper understanding of circuit dynamics.